All right, next section is a nice formula that allows you to compute powers of complex numbers. It's called like DeMoivre's formula. So here the idea is you start with a non-zero number. I mean, this works with zero, but 0 to the power of anything is zero. So that's pretty boring. And your complex numbers is in polar form. So if it's a non-zero number, so absolute value of z, how far away with the argument phi. So what happens if you power that z to the power k? And here k can be positive or negative. So here the idea behind DeMoivre's formula is that if you are powering z by k, you need to multiply or power the distance of z by that power, because every time you multiply distances, or every time that you power by something negative, you divide by that number. So this power of z is then brought on the absolute value of z. And then because during multiplication you're adding the arguments, if you're multiplying by z by itself k times, you're going to add phi to itself k times, or negative k times if you're talking about negative. So anyways, so the polar form can be constructed very, very, very quickly, very nicely. So absolute value of z to the power k times cos of k times phi plus I sine of k times phi is the polar form of the complex number z to the power k. And if you want the Cartesian form, then you just need to multiply z to the power k times cos of k phi, and z, absolute value of z, to the power k times sine of k phi for a and b, respectively. So here we go. So an example. So let's take the complex number 1 plus I, and let's raise it to the power 10. So I only have one example with a positive number, but it works also for negative. So here, the first thing you do when you're powering a complex number by a high power, you write that number in polar form. So I plus I, we've done this example before. The polar form is root of 2 cos of pi over 4 plus I sine pi over 4. So I drew again here 1 plus I, just in case you need a review. So the angle is 45 degrees, so pi over 4. And the distance here, using Pythagoras' theorem, is 1 squared plus 1 squared, which is root of 2. So I have my polar form, and now if I need to raise 1 plus I to any power, like in this example, let's raise it to the power 10. So you take absolute value, you raise it to the power 10, and you take the pi over 4, but you multiply it by 10, not raise it. And then here 10, so root of 2 to the power 10, that's 2 to the power 5, which gives you 32, and 10 times pi over 4 simplifies to 5 pi over 2. So this would be the polar form. If you need just the polar form, by the way, 5 pi over 2 is coterminal to pi over 2. So if we are asking you to have phi between, let's say, minus pi and pi, you would need to readjust. But normally, I don't really give a shit about, sorry about language. I don't care about the polar form. I care more about the Cartesian form. So you can leave the argument as 5 pi over 2. Anyways, so if you bring the 32 inside, so 32 times cos of 5 pi over 2, or cos of pi over 2, this will give you 0. And if you multiply 32 times sine of 5 pi over 2, or sine of pi over 2, you're going to get 1. So this is going to give you 1 times 32, which gives you that 32i. So, and this is extremely powerful, because just think about it. If you were going to multiply 1 plus I to the power 10 the long way by writing 1 plus I times 1 plus I, etc., 10 times, and then superfoiling this would take you forever before you finish. So yes, you can do it the long way, but DeMoivre's formula works for any power right away as one single computation. All right, one more application to wrap up this chapter. At 13.8, we're going to talk about complex roots of quadratics. In particular, I'm really talking about irreducible quadratics, because if your quadratic is reducible, then you can compute roots using what you've learned before. So here we're starting with a quadratic equation. The a cannot be 0, by the way, because if a is 0, then we have a linear equation. and we want to compute the roots. So to compute the roots, basically you use the exact same formula as before, the good old quad formula. So the roots are minus b plus or minus the square root of b squared minus 4ac divided by 2a. And normally when you were younger, if the b squared minus 4ac is equal to 0, is strictly negative, you would say that there's no root. And this is true, but what should have been said is that there's no real root. But now, if you get a square root of a negative, because you know that I squared is minus 1, or plus or minus I to the power 2 is minus 1, you can actually solve this equation and find roots that are complex, even in the case when the quadratic is irreducible. So what you do is you just take the square root of your number. So if you have, for example, the square root of minus 4, because the square root of 4 is 2, you can use 2i or minus 2i as a possible solution. So now even if the b squared minus 4ac part is negative, or strictly negative, that's called the discriminant, you have roots, but they will be complex. Let's just do two examples. It's very straightforward stuff. So first example, x squared plus 1 is equal to 0. Of course, there's no real solution, but if you look at this as a polynomial, so here the coefficient in front of x squared is 1. There's no x value, so the coefficient is 0, and the constant is 1, so c is equal to 1. So the roots are minus b plus or minus b squared minus 4ac. So minus 0 plus or minus the square root of 0 squared minus 4 times 1 over 2a. So the inside here of your square root will give you minus 4, and the square root of minus 4, like a possible root for this possible solution for the square root of minus 4 is 2i. So here 2i divided by 2, we have plus or minus i. And it fits. Like one way to see that your plus or minus 1 is a solution, if you replace x in your original equation by I, you get I squared plus 1, which is minus 1, plus 1, which is 0. Or if you plug minus I squared, you're still going to get minus 1. So both are solution. And a nice cute remark here, before you would say that x squared plus 1 is irreducible since it cannot be factored. But now it can. You can write x squared plus 1 as a product of two linear factor x minus the first root. So suppose I is the first root times x minus the second root. So suppose minus I is the second root. So now you can factor x squared plus 1 with two linear terms, but where the roots are complex values instead of real values. So for the next one, for x squared minus 4x plus 5, so here the a is 1, the b is minus 4, the c is 5. You plug everything in your formula, so your a, your b, and your c. Then when you do the math, you can simplify everything. So minus 4 is 4. The minus 4 squared is 16 minus 20, which we get minus 4 again. It's a bit boring, but that's the way. Divided by 2 times 1, which is 2. And then the square root of minus 4, or a square root for minus 4 is 2i. So the square root of 4 is 2. So you get 2i, divided by 2 everywhere. 2 plus I and 2 minus I are the two possible roots. Again, it's a good exercise to plug the 2 plus I in your original quadratic and see that it sums up to 0. And same thing for 2 minus I. And again here, as a nice little remark, the quadratic x squared minus 4x plus 5, which is reducible, we used to say we cannot factor it. But if you take the first root, which is 2 plus I, so if you go x minus the first root times x minus the second root, now you have a factorization for that polynomial. So actually now every single polynomial can be factored if you're allowing complex numbers to be introduced. And that's it. But it's really just the same old formula, and you're just allowing yourself to work with roots of negative numbers.